Okay, so in this lecture, let's talk a bit about open and closed sets, more specifically closed sets in terms of an arbitrary topological space. Okay, so yeah, so we give the heavy heading as open and closed sets. Okay, so open sets have a very trivial definition in terms of a topological space because so if I recall what the definition of a topological space is, so precisely, so let X be a set, so let X be a set and let we denote a collection of subsets of X as tau, so it's a subset of the power set of X. Okay. And tau is said to be a topology if the following conditions hold. So condition number one is that the empty set and the whole set X, they are both in tau. Number two, tau is closed under arbitrary union, right? Under arbitrary union. So what do we mean by tau being closed under arbitrary union? So that basically means that is if you have a collection, say AI, small I is in some indexing in set capital I, is a collection of subsets of X such that each AI is in tau, then the union of all these AIs ranging over I in capital I is also in tau, right? And number three, that tau is closed under finite intersections. So tau is closed under finite intersection. Okay. Okay, so tau is closed under finite intersection. So this specifically means that it's relevant to what we have here, that if you have a finite family of subsets of X such that each of the elements are in tau, that is if you have a set, let's say AK, such that K belongs to block N. Block N is block N is this collection. So they are the natural numbers 1, 2 till N. Okay. So that is, so if you have this is a collection of subsets of X such that each AK is in tau, then their intersection is also in tau. Then their intersection. So the intersection is obviously from K equal to 1 to N. The case is in tau. Okay. Now this definition is, you might say that it's some generalizations of the observations we have got when we have worked out with open sets in terms of metric spaces, or specifically when we had worked out with open sets in the real number line, in the real field. So when we had studied metric spaces, or when we had studied the real analysis, we had seen there that if you have an arbitrary family of open sets, then their union is again an open set. If you have a finite family of open sets, then their intersection is again an open set. Then the whole metric space is open, and the empty set is also considered to be open. So having some relevance to that, we just claim that any subset of X which is contained in tau is an open set. So elements of tau are said to be open. Okay. Well, this is the very basic definition of open set in relevance to an arbitrary topological space. And from here we also have the definition of what we call a closed set. So let X tau be a topological space. That means X is a set and tau is a topology defined on X. That is, tau is a subset of the power set of X, which satisfies all the three axioms I just wrote. So let X tau be a topological space. Be a topological space. Then U is said to be closed. Is said to be closed if and only if the complement of U, that is X minus U, is in tau. That is, U is said to be closed if and only if it is open. So that is the precise definition. Some very trivial examples of a topological space is being the, let's say, the discrete topological space. That is, if I consider tau to be all the power or all the subsets of X, okay, for some set X, then obviously X tau is a topological space, right? Because if you consider any arbitrary family of subsets of X, then their union is also a subset of X. If you consider a finite family of the subsets of X, then that's also a, their intersection is also a subset of X. X is a subset of itself, so it belongs to the power set of it. Null set is also a subset of X, as as declared, you might say. So it's also inside 2 to the power X. So it's just a topological space. One thing to obviously notice here, that since tau contains all subsets of X, so every element in tau is obviously open, but it's closed at the same time, right? Since tau contains all subsets of X, therefore for all elements in tau, U complement is also in tau, because U complement, if you consider a set from tau, that will surely be a subset of X, so its complement will also be a subset of X. But if it is a subset of X, it must be in tau, because tau contains all the subsets of X, right? So therefore every element in tau is both open and closed. Or rather, I should be more precise, that every subset of X is both open and closed, we can say, right? Because tau contains every subset of X. So therefore every subset of X is both open and closed. Such sets are often called Klopen sets. Okay. Also called Klopen sets. Okay. This topology is called the discrete topology, where the topology is specifically the power set of X. So this is called the discrete topology. Discrete topology. One more trivial example is if tau contains only X and phi, that is null set. This is called the indiscrete topology. Indiscrete topology. So what are the only open sets of this set X? Tau is obviously, X tau is a topological space, right? The topological space. The only open sets of X and tau are X and the null set itself, right? So the only closed sets will be, so what is X complement? It's the empty set, and what the empty set complement is X. So the only closed sets are also the whole set, or the whole space, you should say, and the empty set, right? We can have, pretty important examples, non-trivial examples, I should say. Suppose I consider this set, that let X be a set. So we define tau as follows. Define tau as, so it's the collection of all subsets of X such that U is empty or U complement is finite. Okay. And does this form a topology? It's indeed a topology, right? Because if you consider an arbitrary union, then, so let me just give a hint to it. Suppose you have an arbitrary union of elements, let's say union over I in capital I, ui, where each ui is in this topology. So if you consider this union, what's the complement of it? So it's, you have the De Morgan's theorem, right? So it's over the indexing set capital I, so it's the intersection of UI complements, right? Right. Now, obviously, each UI complement is finite because UIs are elements from tau, and tau contains only those sets whose complement is finite. We are obviously assuming that none of these UIs are empty. That will be more precise. So each of these elements are finite, right? So the intersection is also finite, right? And same thing you can do for the intersection part also. If you just need to consider the complement of it, that's the only thing you need to do. Okay. So this indeed forms a topology. This is called the I think it is called the finite complement topology. Yeah. It's called the finite complement, or it's also called the cofinite topology. It's called the cofinite topology. We have a similar topological structure where you just define the topology as subsets of X such that it's empty or its complement is countable. In this case, it's called the co-countable topology. Co-countable topology. And in both these definitions, we obviously assume that phi complement is the whole of X. Clear? Okay. And there are obviously more examples. For example, if you consider the most trivial example, then I would say if you have the real numbers, let's say, if you have R, let me just write it in the usual notation. So you consider the real numbers. Consider R, okay, and consider these open intervals. Open intervals are the open intervals in R. So construct tau as the union over these open intervals, all possible unions over these open intervals. So it's union over these open intervals. Or I shouldn't write it like this. So let tau be the collection of all possible union of these open intervals. And that also forms the topology. This topology is called the standard topology. This topology is called the standard topology on R. And this is the exact topology which we have studied in real analysis, because remember, in real analysis we had considered the open sets to be of this form, right? To be with the very basic sets where we used to consider to be of this form, right? Okay. So yeah, I think we are okay. Let us discuss one more example, which is also quite relevant. We can consider the concept of a metric space. Okay, so let XD, let this be a metric space. Then recall you had this definition. So UXR is defined to be the collection of the elements Y in X such that distance of Y and X is less than R. Right? We used to call this the open ball of center at R. Sorry, at center at X and radius R. So again, if you consider all possible unions of these open balls over the elements X in capital X, then that also forms a topology. That is usually called the standard topology of a metric space. Okay, we also use the term topology generated by the open balls. In this case, it's called topology generated by open intervals. Okay. Clear? So yeah, so let's now move on to the concept of closed sets. I think we have discussed enough about topologies. Okay, so I had given the precise definition, right? So a subset of a metric space, a subset of a topological space X is said to be closed if its complement of some element in the topology. That is, it's complement of an open set. Clear? So let us a few examples of closed sets. So if you consider the standard topology on R, then observe that the closed interval is closed because because this closed interval has, so what is the complement of this closed interval? So it's basically this open set, right? So it's minus infinity to A union of B to infinity. So it's an union of open intervals, right? Because we had defining the standard topology, we had considered to be unions of those open intervals for all elements A and B ranging in R, right? So this is indeed elements from tau. So their union is also an element from tau. So it's indeed so the complement is indeed inside the standard topology, right? So that means it's closed, right? Number 2, we had discussed what we call the cofinite topology, right? Cofinite topology, yeah, finite complement topology. I was saying correct. So obviously observe that what happens. So what is the definition of a closed set? So a subset of X, let's say A, is closed if and only if its complement is in tau. And we know how a cofinite topology is defined. So it's the collection of all those elements, all those non-empty sets, let's say non-empty subsets whose complement is finite. So therefore it's obvious that in case of a cofinite topology, every finite set is closed, right? Every finite subset, I should say. Every finite subset is closed, right? And obviously the set itself is closed as well. Is closed along with the set itself. Right? Then we will also discuss the fact that if you consider the discrete topology, then every subset is both open and closed. That is, it's a clopen set, right? One set. Okay. Okay. Now observe the following that. So let me just explain this a bit. That we know that topology is closed under arbitrary union and finite intersection, right? Therefore, we can say that arbitrary, since the elements in topology are called open sets, so arbitrary union of open sets is open, right? Because arbitrary union of elements in tau is still in tau, and finite intersection of open sets is open, right? But doesn't it immediately imply that finite union, or let me just speak that, doesn't it immediately imply that arbitrary union we have, right? So we can say that arbitrary intersection of closed set is closed, and finite union of closed sets is closed, right? Why? Suppose we have an arbitrary union of some family AI. What is the complement of it? So it's intersection over I in I, AI complement. Now suppose this AI is open, right? Then this is closed, right? This indexing family is arbitrary. So this is indeed an arbitrary intersection of closed sets. Now we know arbitrary union of open sets is open, right? So this is open, right? This is open, So this is open, that means this complete part, the complement of it is closed, right? So that necessarily means that arbitrary intersection of closed sets is closed. Similarly, we can frame this up, right? Because if you have a finite intersection, then its complement is finite union, right? Right. So if this is open, then this is closed. So it readily follows from here. So I can obviously summarize this as a theorem. So let me just summarize this as a theorem. So let X be a topological space. Let X be a topological space. Then the following holds. Then the following holds. So number one, that phi and X are closed, because, and this is readily because phi complement is X and X complement is phi. So since phi is in tau, phi complement must be closed, so X must be closed. Since X is in tau, that is X is open, so its complement must be closed, that is phi is closed. Right? Number two, what we said is that finite union of closed sets is closed, right? And the third point we had is arbitrary intersection of closed sets is closed, right? So if you have an arbitrary intersection of closed sets, then it's closed. Arbitrary intersection of closed sets is closed. Okay. Yep. So the proof is also clear, I guess. Now we have something called a subspace topology. So let me just give a brief intro to it. So if X tau is a topological space, then if you consider a subset of it, then Y can be made into a topological space by what we call a subspace topology. So we define tau Y to be the collection of sets which are, let's say, the sets, let's say uy, such that these uys are the intersections of u and y, where u belongs to tau. Okay. So what is this basically? So the basic literal sense of this is that open sets in the subset Y are intersections of open sets in the space X with Y. That is the basic definition. Okay. Or we can simply denote this as the collection of elements of the form U intersection Y, such that U belongs to tau. Right? Right? So tau Y is a topology on Y. So tau Y is called the subspace topology. So if I be very literal, then I should say that open sets in the subspace topology in the subspace topology are intersections of Y with open sets of X. That's the precise part. Clear? So one more way of having this into consideration is that if uy is open in Y, then there exists u open in X, such that uy is written as u intersection Y. Right? So this is, I guess, more mathematically important. So now let us define closed sets for subspace topology. So let me just consider this as a theorem. So let Y be a subspace of X. That is, Y is a subset of X with a subspace topology defined on it. So Y is a subspace of X. X is also a topology by consideration. That's quite trivial. I'm not specifying that every time. Then a set A is closed in Y if and only if it equals the intersection of a closed set of X with Y. Clear? So let us prove this. I think this is quite relevant with how subspace topology was defined in terms of open sets. So quite related, I should say. Okay. Let us start with this. Now, first observation is obvious that if you consider a set from tau y, that is, so if B is open in Y, then, or I can simply write it as an if and only if condition. Right? B is open in Y if and only if B is equals to some U intersection Y, where U is open in X. Okay. Okay, first we assume that a set A is intersection of a closed set of X with Y. So let A be given as C intersection Y, where C is closed in X. Where C is closed in X. Okay. Okay. Now, if C is closed in X, then that implies X minus C is open in X. Right? But if X minus C is open in X, then we can say that X minus C intersection Y is open in Y. Is open in Y. Right? But what is X minus C intersection Y? So X minus C intersection Y is nothing but Y minus A. Right? So this is open in Y. Right? Now this is elementary set theory. But Y minus A is open in Y means Y is closed. A is closed in Y. Right? That's quite obvious. Conversely, what happens? Conversely, suppose A is closed in X. Suppose A is closed in Y. So that implies Y minus A is open in Y. Right? But that implies Y minus A is the intersection of U with Y for some open set U in X. Right? But from here it's obvious that A can be written as X minus U intersection Y. Right? But X minus U is closed because U was open. It's closed. Right? So it's intersection of a closed set. Right? So that's the proof. One obvious observation from here we can say is that if you have a subspace of some topological space, then some set being closed in that subspace doesn't necessarily imply it's closed in Y. Right? So it needs to be an intersection of a closed set with Y. Kind of that's all. Okay. So the next immediate theorem is in this way. I can also consider this to be a corollary of this theorem. Let me just state it as a theorem itself. So let Y be a subspace of X if A is closed in Y and Y is closed in X, then A is closed in X. Right? So how is the proof going? So A is closed in Y, right? A is closed in Y. So that implies there exists a closed set of X. There exists a closed set of X, say C, such that A is the intersection of C and Y. But C is closed in X. Y is also closed in X. Intersection of closed sets, finite intersection of, arbitrary intersection of closed set is closed. So finite intersection of closed set is again closed. Right? So Y is closed in X. So that implies C intersection Y, which is equal to A, is closed in X. because if you consider a set A which is closed in Y, so A is necessarily a subset of Y, so A is obviously a subset of X because Y is a subset of X, indeed a subspace of X, right? So C intersection Y which is equal to A, so it must be closed to X, right? Now our goal is to have the definition of a closed set which is in close relevance to the definition of closed sets in case of arbitrary metric spaces. So if I just quickly recall, then we had the definition of what we call the closure of a set and what we call the interior of a set. We won't need the concept of interior much at this moment because we are discussing about closed sets, but let us define both. So let X tau be a topological space and let A be a subset of X. We define the interior of A, which is also denoted as A naught, you might say. So this is defined as the union of all open sets contained in A. And we define the closure of A, which is denoted as CL of A, or you can also denote it as like A bar. Okay. So it's defined as the intersection of all closed sets containing A. Containing A. So interior of A. So this is the interior of A. So we have a union of all open sets contained in A, and the closure of A is the intersection of all closed sets containing A. Okay. So it's specifically, you might say, it's the smallest closed set containing A, because intersection of arbitrary intersection of closed sets is closed, right? So it's the smallest closed set containing A. So it's obvious from the definition that the interior of A is contained in A, which is contained in the closure of A. And the interior of A is open by definition because it's arbitrary union of open sets, and the closure of A is closed by definition because it's arbitrary intersection of closed sets. So this is by definition closed, and this is by definition open, right? We say that A equals to A, the interior of A, when A is open, and A is said to be closed if A equals to A closure. Okay. This is quite relevant, right, to what we had studied. Okay. Okay. So, because if you quickly recall the so these two statements are in relevance with the definition of closed sets and open sets as we have studied in case of arbitrary metric spaces, right? So let us go through a quick theorem regarding a closure of a set. Theorem. Let Y be a subspace of X. Let Y be a subspace of X. Let A be a subset of Y. Then the closure of A in Y is a closure intersection. So this where just specify it, where A bar is the closure of A in X. Okay. Now one thing is quite obvious, that A closure is closed. So that implies A closure intersection Y is closed by the theorem which we had proved. Right? So we don't need anything about the closedness of A bar intersection or closure of A intersection Y. Okay. So suppose, so the obvious start to this proof should be, we assume the closure of A to be some set B, and then we eventually prove that B must be equals to this set. So let B be the closure of A in Y. Okay. Right. But that immediately implies that the closure, that B is closed, right? Or we can say it in this form. I should not immediately imply B is closed. I should say that now since A bar is closed in X, which is the observation I had here. So that implies A bar intersection Y is closed in Y, right? Right. Now, so since A is contained in A closure, A is also contained in Y by assumption, by hypothesis issues. That implies A must be contained in A closure intersection. But what is B? So B is the smallest closed subset of X, or I should say subset of Y in this case, because B is the closure of A in Y, which contains A. Or I can just immediately say that since B is the smallest closed subset of Y containing A, therefore since A is inside this set, B must also be inside this set, right? Right? B is indeed closed because B is the closure of A in Y. B is indeed closed. So, so it suffices to show, right? So it suffices to show that A closure intersection Y is contained, right? Okay. Now B is the closure of A in Y, right? So that means B is closed in Y. So B is closed in Y by hypothesis, because B is assumed to be the closure of A in Y. Right? So that implies there exists a closed set, say C, right? So that implies there exists a closed set C in X such that B can be written as C intersection Y, right? Right. Now B is the closure of A in Y, right? So B is the closure of A in Y, and and A is also a subset of Y. So A is in B, A is in Y. So A must also be in C, right? Now C is the closed set, or I should say is a closed set in X containing Y. Containing A, right? And by definition, so by definition, the closure of A is the smallest closed set containing A. So that implies the closure of A must be inside C, right? But that readily implies that the closure of set intersection Y must be inside C intersection Y, and C intersection Y is B, right? So the closure of A intersection C is contained in B. Here where B is contained in the closure of A intersection Y. So both of these statements, so suppose this is 1, this is 2, therefore 1 and 2 imply that A closure intersection Y must be equal to, that is our requirement indeed, right? Okay. The next theorem is pretty important from the point of view of the definition we had studied in terms of arbitrary metric spaces. So the theorem says that let A be a subset of the topological space x tau, then x belongs to a closure if and only if every open set U containing x intersects A, right? So recall what we have started in the metric spaces. So we had said that x is in a closure if and only if for all r greater than 0, the open ball with center at x and radius r intersects A. Intersects A means it is a non-empty intersection, right? So this is what we are actually proving here, because if you consider all the open balls centered at x and with radius r, so that indeed gives you the collection of all the open sets which contain x. Indeed, basically the open sets containing x are typically called the open neighborhoods of x, right? So open sets containing x are typically the open neighborhoods of x. The open neighborhoods of x. So this was indeed what we studied. Further, if I talk about simple real analysis, then we had that for all epsilon greater than 0, x is in a closure if and only if for all epsilon greater than 0, x minus epsilon, x plus epsilon, intersection A is not. So this was considered to be the open neighborhood of x in the real life, right? So this is quite in relevance to these definitions, right? So let us quickly prove this. We prove this by the process of contrapositiveness. We use the method of contrapositiveness. So what is typically the contrapositiveness? So it's basically that if P implies Q, then Q naught implies P naught. We can say this as that Q implies P, P implies Q if and only if Q naught implies P naught. So we prove this. That automatically proves this. So what we do is that we let x be not in a closure. We need to show that if x is not in a closure, then there exists some open set U or some open neighborhood of x which does not intersect A. That will immediately prove that if every open set U containing x intersects A, then x must be in a closure. Clear? So we are proving this part. So let x be not an element of a closure. Consider the set x minus a closure. As let this be U. Okay. Then a closure is by definition a closed set. So x minus a closure is by definition open set. Therefore, U is open. Further, since x is not in a closure, x is surely in x minus a closure. That means x belongs to U. Therefore, U is an open set containing x. Right? We need to show that U does not intersect, and that is also quite obvious, because since x is not in a closure, that implies x is not in A, because A is contained in a closure, right? As A is contained in a closure. Since U is defined as x minus a closure and A is contained in a closure, so that immediately implies that U intersection A is empty. But U is a open set containing, so U does not intersect A, right? So that implies, so this is what we had, right? So that's the end of the proof of the first part. So that is U does not intersect A. Let's prove this part. I should not use the symbol here. We typically use this at the end of the whole proof. So how do we do this? We can do this. Suppose we consider a set U of this form. Okay, so let U be an open set in X such that X is in U and U does not intersect. Okay, U does not intersect. Let or rather I can think of it like this. Since U is open, X minus U is closed. Since U intersection A is empty, so that implies A must be completely contained in the complement of U. Right? But that means the closure of A is contained in the complement of U. Why? Because the closure of A is by definition the smallest closed set which contains A. Right? So that implies X is not in A closure, as X was in U. Right? So X must not be, X cannot be in A closure. So that's the end of it. Right? So let this lecture be up till this much. In the next lecture, we will be discussing about the concept of limit points, and then we will be moving on to a very important set of topological spaces called the Hausdorff spaces. Okay, that will be a quite interesting discussion. So meet you guys in the next lecture.